start talking about the elements that exist in nature. So elements, all things are made up of atoms. That is, all substances of any type are made up of atoms. And those atoms are of various sizes and shapes, etc., that are called elements. And in nature, they can exist in their pure form. In their pure form, this table is representing what their configuration would be. And I'll talk about this in a sec. But in most natural forms, they are existing, interacting with each other. And we'll talk about how that is likely to occur. But let's just say that they were existing in their pure form. We'll talk about their basic atomic structure. Okay, so if we're looking at the basic atomic structure, this is a representation of an atom. Let me back up here. You can, if you want to, you can write down everything I have on the paper and then listen. Okay, so we're going to talk about this basic atom here. This basic atom, an atom is made up of a central core. Usually in chemistry, this is called the nucleus. The nucleus, we don't use that term as much in biology because in biology, a nucleus is the center part of a cell, or not necessarily the center, but it's a control center for the cell. And so central core is sometimes used in bio to talk about the central part of an atom. This is made up of most of the mass of particles or structures called the protons, which are positively charged, and neutrons, which don't have a charge at all. And then they have electrons, which are negatively charged and attracted to the positive protons that are in an orbit around the outside edge. Now, because they're in an orbit, they're moving, and that means that they cannot be very close, or they are as close to the central core as they can be and still move and not cause friction. So that is a certain distance away. It's represented by Avogadro's number. If you have taken chemistry before, don't really need to know that for this class, okay? Now, electrons don't really just go in one single line around that central core. Instead, they go all over the place at a certain distance around that central core, and this is called the orbital cloud. And you might have seen the atomic energy or something like that represented by this symbol, or some, you know, it's not very well drawn, but some symbol that looks similar to this. And that's because the electrons are, if you were to look at an atom, it would look fuzzy, like you would hardly see that central core. Now, the central core, as I was saying before, is making up most of the mass of the atom. So that's made up of protons and neutrons. So this is going to add to its weight, really. And the other part of the atom, the electrons, don't actually have that much mass, even though, generally speaking, the number of protons and the number of electrons are equal. So if it had one proton, it's going to have one electron. If it has 6 protons, it's going to have 6 electrons, etc. All right? Now, the atomic number is the number of protons. That number is represented in this periodic table in the bottom left-hand corner. So this one right here has 1 proton. This one right here has 3. This one right here has 11. And you notice that all of these have different ones. As you look at this periodic table, you can see that 1 over here is the smallest one. And as I look down here, this is the largest one down there. And you read this table from left to right. This one and this one representing the first energy level. These guys representing the second energy level, which we'll talk about in a minute. This is the beginning of the third energy level, and then some of these are going into the fourth energy level. All right, so anyway, we'll talk about what energy level is in just a second. So generally speaking, the number of protons and the number of electrons are equal. The atomic weight, which is in the top left-hand corner of this, up here, this is the average weight of all the naturally occurring forms of hydrogen that exist in nature in their pure form. We'll talk about what that means in just a second. But just so you know, the atomic weight is the number of protons plus the number of neutrons. Now notice that the mass and the weight are similar, and because of that, they're sometimes used interchangeably, okay? Now the electrons, being the outer part of the atom, are the most likely parts to interact with something else. In other words, they're the most likely parts to interact with another atom, either of the same type or of a different type, and they could be lost, gained, or shared, and we'll talk about how that works in a little bit. Okay, now in terms of, you notice on this periodic table how all of these elements are represented by a letter or sometimes two letters. Those words are, or the letters they're representing is usually the word that we know it by. For example, this is hydrogen. H for hydrogen, that's easy. B for boron. C for carbon. N for nitrogen, oxygen, phosphorus, sulfur. Those are the ones that you need to know for biology, so it makes it fairly easy. Some of the other names, for example, Na for natric, this is sodium. Natric is, I believe, the Greek word for sodium. I might be wrong about that, but anyway, it's an older language that sometimes gives you the names of these things. And sometimes they have, for example, Al for aluminum or silicon, etc. Okay, so looking at this, you need to know the atomic number of each one of these. I sometimes call this schnapps, all right? So you need to know carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Memorize the atomic number of these guys. You also should know the configuration of these atoms. In other words, how do the protons and electrons pack in? Now we call that, the way that they pack in means that how are they going to exist in terms of where the protons are and where the electrons are. Now right for this argument, I'm going to ignore the neutrons. Now the reason is because the protons and